All right, so this is the finals key workout. I'm going to try to explain everything as clearly as I can for every single problem. It might get a little repetitive here and there, but we really want to make sure that you understand what's going on here. And so the first part of the review sheet is the periodic table. And the periodic table here includes some naming as well. And so here we have given ionic compounds, name the compounds. And so with ionic compounds, really what you're doing is you're breaking up into two ions and then naming each of those ions. And so the good rule of thumb is that if the first element's a metal, that's an ion, and the rest of it's another ion. If the first element isn't a metal, like a polyatomic, then that's the ion, and then the other element's the ion. And so what you see here is you see something like NH4Cl. Well, NH4 is ammonium, and then Cl is chloride. BeSO4, beryllium, sulfate. These are the polyatomics that you have to know: ammonium and sulfate, etc. So 3 MgCl2, that's magnesium chloride. Notice that for a lot of these formulas, we don't write how many of each we have because these ions have specific charges, and in ionic compounds you have to equal 0, so there's only one possible simplest ratio between the ions here. So for Mg and Cl, Mg is always 2 plus, Cl is always 1 minus, so therefore the ratio is always 1 Mg to 2 Cls. Okay. NH4NO3, that splits up into ammonium nitrate. 5 SR3PO42. Again, notice that we are not really even acknowledging the subscripts here because they're not necessary in naming. Now, the one scenario where it is necessary is when you have a transition metal. Because when you have a transition metal, you have to state in the name what the oxidation number or the charge is, because the reader won't know just from the name. Because Fe can be 2 plus or 3 plus. In this case, it is iron 2 sulfate. Because there's one sulfate, which is 2 minus, so then iron must be 2 plus to zero that out. 7 MgNO3, you revert back to just your naming here. Magnesium nitrate. And then NaOH is sodium hydroxide. Now, going the other way, now you're given these names, and then you have to identify the ions, which then you form into compounds. So, for barium nitrate, barium is Ba2 plus, nitrate's NO3 minus 1. So, you have to have 1 Ba for every 2 NO3s. 3 here. Ammonium, NH4 plus, SO4 2 minus. So you need to have 2 ammoniums for every 1 sulfate. Notice I only use parentheses on polyatomics when I have more than one of them. Is it wrong if you put the parentheses around like SO4 right now? No, not necessarily, but it's just not needed. Okay, 4, aluminum hydroxide, Al3 plus, OH minus means AlOH3. Calcium phosphate, Ca, for this, the least common multiple is 6. So we need 3 calciums and 2 phosphates. Cesium, I think. Sorry, that's a typo on number 6 on the key. This should be cesium 1 plus and nitrate 1 minus. So that's just CsNO3. So that's a mistake on the key. Just as a note for those of you checking. calcium sulfate, Ca2 plus, SO4 2 minus, CaSO4, beryllium sulfate, Be2 plus, SO4 2 minus, so that's BeSO4. Sodium carbonate, Na plus, carbonate is CO3 2 minus, so that's Na2 CO3. Magnesium phosphate is 2 plus and 3 minus, so we need 3 Mgs and 2 phosphates. And then calcium is that same idea here, 3 calciums, 2 phosphates. Now, the next level in which you do this is now you start converting your words into equation form, where now you don't just have one substance, you have multiple substances that you are having to combine together. So it's still a good idea to write each species out separately, because when you do that, then you can balance as necessary and make sure that you have the right formulas, because if you don't have the right formulas, you can't balance. Your balancing does not rely on everything being equal right away. So don't try to make it the same on both sides. So zinc plus lead 2 nitrate. Okay, lead 2 nitrate is Pb2 plus and NO3 minus 1. So that is PbNO3 2. And then forms zinc nitrate. Zinc is 2 plus, NO3 is minus 1. So that's zinc nitrate, ZnNO3 2 plus lead. In this scenario, it happens that they are equal and everything's balanced already, but that's a coincidence, not the norm. Because if you look at the second one, aluminum bromide, Al3 plus Br minus, plus chlorine gas, which is Cl2, yields Al3 plus Cl minus, yields Br2. You've got to combine these now. Okay, so this is AlBr3 plus Cl2 yields AlCl3 plus Br2. And just a reminder, remember the way I balance is I write substances underneath each substance to make sure it balances. So in this case, what we find out is the least common multiple is we need 3 Br2s and 2 AlBr3s, which means I need to have 2 AlCl3s and then 3 Cl2s. So this is 2, 3, 2, 3 as your formal balancing that equation. Okay, 3 sodium phosphate plus calcium chloride, which is Ca2 plus Cl minus 1, yields Ca2 plus and phosphate 3 minus, and sodium chloride, which is NaCl. So I write all my ions out first. It helps me organize my thoughts, and then I form my compounds from that. CaCl2 yields Ca3PO4 2 plus NaCl. Okay, and I'm not going to demonstrate all these balancing because we do more balancing later on, but since we're already here, I'm going to show you that here. So notice I have 3 NAs on the left, which means I have to add more NAs in the form of NaCl on the right. Now, I notice that I have 3 CAs, so I have to add 3. I have to have a total of 3 CaCl2s on the left to balance out the Ca. Now, what happens is, because now I have 6 Cls on the left, I need to add more NaCls because that's the only source of Cl on the product side. So I have to keep adding NaCls to balance that out. And as a byproduct, that means I need to add another Na3PO4. Now, this balances 2, 3, 1, 6. And this balancing method works for every single type of reaction, but the only time where I think it could be difficult is for combustion, because sometimes combustion you have really high coefficients, and so combustions you may want to look at doing it an alternative way, but all of the reactions, there's not a scenario where I think that you can't do this for anything provided to us. Okay, 4. Potassium metal, that is K by itself, reacts with chlorine gas, which is Cl2 because it's diatomic. And we form potassium and chloride. So this is K plus Cl2 yields KCl. And there's your balanced equation. 5. Aluminum plus hydrochloric acid, which is H plus and Cl minus, yields aluminum chloride, which is Al3 plus and C minus, plus hydrogen gas. So this is Al plus HCl yields AlCl3 plus H2. So we end up having to balance it as such. 6. Copper plus sulfuric acid, which is H plus and sulfate, yields copper 2 sulfate. So copper 2 plus, sulfate 2 minus, plus water, plus sulfur dioxide. Sulfur dioxide is a covalent compound, so it literally tells you how many of each substance you have. So Cu plus H2SO4 yields CuSO4 plus H2O plus SO2. Turns out here that to balance this, you actually need 2 H2SO4s and 2 H2Os. Because the Cu is already balanced, and so since you have 2 SOs on the right, that means the S is on the right, and you only have one source of H2SO4 on the left, that has to be increased, which then increases the amount of waters that you have. 7. Hydrogen gas, which is H2, plus nitrogen monoxide, which is NO, because nitrogen monoxide is one N and one O, yields water and nitrogen gas being a diatomic. So it turns out it is 2, 2, 2, 1. Okay. Next unit is bonding. Okay, with bonding, what you're doing here is you are pairing up electrons, whether it's donating and gaining them or sharing them. You're drawing Lewis structures for these molecules. And so, for example, if you have the bond between an Mg atom and a Cl atom, well, this is a metal and this is a non-metal. So therefore, you're going to be transferring electrons in the form of an ionic bond. So you start with Mg with 2 dots and Cl with 7. Okay. Actually, I'm going to color change this so it's easier to kind of track the electrons here. Now, Mg is able to donate 1 electron to the chlorine here, but now this Mg still has 1 electron left over. So in other words, you need to have another chlorine here so that the other electron can donate there, which then results in having an Mg ion, which has 0 valence electrons, which is 2 plus, and a Cl atom, 2 of them, that have a 1 minus charge. Which then equates to a formula of MgCl2. And we do this for each of our species here, or each of our examples, Mg and S. Well, Mg has 2 dots, S has 6. Let's clear that up a little bit. 1 on each side before you double up. Makes things a lot easier for you, because then you can see which ones are paired and unpaired. Okay, so Mg donates 1 here and donates 1 here. So in this case, you only need 1 of each. To get the transfer electrons. So then your formula is MgS. 3, Al, and F. Al has 3 electrons. F only needs to accept 1. So therefore, there needs to be 3 Fs to be able to accept all the electrons that aluminum is giving away. Which then gives us the formula of AlF3. So the middle column is your final ionic form. So if you're asked to draw the Lewis structures of the ions, this is what you want to show. This is the chemical formula, or the formula unit of the compound. Last but not least, Ca and I. It is getting repetitive, but you see the idea that you are trying to accomplish with each of these ionic bonds. Let me erase that dot. It's really hard to see. So you need 2 I's here to accept the calcium electrons. And we didn't end up doing one where you need more than one metal, but it is possible to need more than one metal as well. To get the formula. CaI2. Okay. Covalent naming. Now, what's nice about covalent naming is that you don't have to figure out anything about the structure or the charges to figure out the formula, because in covalent naming, it is a very literal translation. And so you just look at the prefixes. And so, and when you're naming it, you just literally tell how many are each in the name. So, for example, N2O5 is dinitrogen pentoxide. The di means 2, pent means 5. SeBr6. The only time you don't use a prefix is the first one if there's only one. So this is sulfur hexabromide. Okay. CH4 would be carbon tetrahydride. 4, this is a typo, it should be C6H6 like a subscript, but it'd be hexacarbon hexahydride. And we'll continue doing that for the rest of it. Phosphorus hexafluoride. 6, boron trifluoride. 7, diphosphorus tetraiodide. 8, disulfur trichloride. 9, nitrogen. Notice there's no mononitrogen. Nitrogen dioxide. Diphosphorus pentoxide. Oops, did I skip one? No, I didn't. Sorry. Oxygen difluoride. 12, carbon monoxide. 13, bromine trioxide. 14, boron mononitride. And 15 is carbon tetrabromide. Now, a great way I would say to practice covalent naming or even ionic naming is to write your answers on a separate sheet of paper and then try to go back later and look at just your answers and try to write the formulas from your answers. If your formulas from your answers aren't the same as the ones on the worksheet, then you did something wrong or you remembered something wrong in your naming pattern. So just be careful about that. Okay? I'm going to go kind of quickly through this because it is fairly straightforward here with all the prefixes here. H2O, N2O3, CCl4, carbon dioxide CO2, trinitrogen tetroxide is N3O4, 6 nitrogen monoxide is N2O, 7 tetraphosphorus decoxide is P4O10, 8 selenium trioxide, 9 iodine heptafluoride, IF7, sulfur hexafluoride, SF6, sulfur dichloride, SCl2, disilicon hexabromide, dichlorine heptoxide, and pentaphosphorus decoxide, which is P5O10. I saw that. P5 pentaphosphorus decoxide. Now, with the Lewis dot structures for covalence, instead of donating and accepting electrons, you end up sharing electrons. And when you are trying to work these out, you want to pair the unpaired electrons that are illustrated in each of your structures here. And so, for example, in number 1, the first element generally goes in the middle unless it's hydrogen. So CO2. C has 4 electrons. And O has 6. Now, I'm just drawing the dots on the sides so it's the most convenient to show the work, but it doesn't matter which side you draw the dots on, because all you're doing is trying to pair up any electrons that are by themselves so that everything is complete. And so when you do that, you end up with a structure where you have lines for each of those pairs you paired up, and then the leftover dots that weren't bonded on each structure. So like H2O, O has 6 dots, H has 1. So you pair up your unpaired electrons, and then you leave all the other electrons alone when you redraw it. HI. H has 1. I has 7. They pair. And notice I draw the lone pairs around the I that are still not bonded together because those are important. 4. NH3. N has 5. Each H has 1. So each hydrogen shares a pair of electrons, with the nitrogen here. And we'll continue on doing that for the rest of these structures. 5. As such. HCN. C is in the middle. N is on the side. So we pair up 1, pair up 2, pair up 3, and pair up 4. You shouldn't have any lone electrons by themselves if you're covalently bonding. And where I put the dots on the end doesn't really matter. I can put it on top, the side, the bottom. It doesn't really matter. And last but not least, SeF2. F has 7. Se has 6. So therefore we pair up 1, pair up 1. And we get that structure here. Okay. The next one is types of reactions and balancing. Okay. And so what you'll see here is identifying the types of reactions and balancing equations and also predicting products as well. Okay, so all of this is designed to help you balance equations and identify the reactions and predict the products of word equations, because you'll be expected to do that in other problems in stoichiometry as well, and you can't do stoichiometry right if you're not balancing equations correctly for this. And so I will demonstrate on some of these how they end up needing to be balanced, the same technique that I've done before, just to make sure we understand. So the first section, you're given the products and the reactants. So you're just focusing on balancing the equation. Okay, well, 3 H's on this side means I need to add more H's on this side. And then 3 NA's on this side means I need to add NA's on this side. Now my BR's are equal, my H's are equal, my NA's are equal, my PO4's are equal. So my overall balanced reaction is 3, 1, 1, 3. And this is a double replacement or displacement reaction. Okay. Because you have two compounds that are swapping partners. 2. H2CO3 going to H2O plus CO2. Now this is already balanced, and it is a decomposition reaction because you have one compound breaking down into smaller compounds here. 3. Mg plus Fe2O3 yields Fe plus MgO. Well, we need an Fe here. We need 3 O's here, which means we'll need that. So it is 3, 1, 2, 3. And this, because it's one compound and an element, and they're swapping partners, this is single displacement. Okay, so 4, you have C2H4 plus O2 yields CO2 plus H2O. So in this one, it is still fairly easy. H2O here, and then CO2 here. And so you count, you have 6 O's, so that means you need 3 of these. So it's 3, 2, 2, 1. And this is combustion, because you're reacting with oxygen to form oxides. Okay. 5, PbSO4 yields PbSO3 plus O2. Balance this. And it is decomposition. 6, H2 plus I2 yields HI. We need 2 HIs. So therefore this is synthesis. 7. H2O plus SO3 is H2SO4. It happens to already be balanced. And this is also synthesis. Last one, H2SO4 plus NH4OH yields H2O plus NH4 2SO4. In this case, what you really want to think about you want to think about water as HOH, if that helps you kind of think about the balancing, because it's hard to see the OHs here, but the OHs are inside the water. And so that's, if it helps you to write water as HOH when you're balancing, I think that will help. I think that's a good idea if you're having trouble seeing it. And this is a double displacement reaction. Now, for the second part, you've got to identify the type of reaction so you can figure out what is happening in each of these reactions. And for this, a lot of times with displacement reactions, you're going to use the box method, at least from what I taught. And so the box method allows you to swap ions and charges easily based on their positive and negative aspect, which then helps you predict the products. So you have Ag here and CuSO4. What I do is this. I place my species into a box here. So Ag plus 1 would go up here because that's the ion charge of Ag. And then on the bottom would be Cu 2 plus and SO4 2 minus. So it organizes the ions according to their reactants. And to figure out the products, you will crisscross, go diagonal, and make the new formulas. And so here it would be Ag2SO4, and since Cu is by itself, you don't write a charge on it. You just write Cu. Okay, and so this is single replacement. And we'll do that a couple more times in these practice ones. NaI plus CaCl2 yields Na plus 1, I minus 1, Ca2 plus, Cl minus 1. Okay, so we go diagonally. So we get NaCl, because Na plus 1 and Cl minus 1, and then CaCl2, which is 2 plus and 1 minus respectively. So then we have to balance 2 and 2, and this is a double replacement or double displacement reaction. 3, anytime you have two elements by themselves, it's going to be a synthesis reaction. In this case, we're synthesizing into water. And so we double this and double this, and this is synthesis. Okay, 4. HNO3 plus MgOH2. So H plus and NO3 minus, Mg2 plus and OH minus go diagonally, forms MgNO3 2 plus H2O. So we end up needing 2 of each of these, and this is double displacement or replacement. Okay, and we're going to continue to do this for all of those problems here. AgNO3 plus BaSO4 Ag plus, NO3 minus, Ba2 plus, SO4 2 minus, So, oops, yeah, that's right. Okay, so then my products are Ag2SO4 plus Ba NO3 So we balance here. Actually, there, and so we get double displacement again. 6HCN plus CuSO4. I'm going to kind of pick this up a little bit. CuCN2 plus H2SO4. So this is 2, and this is double displacement again. Most of these reactions are double displacements when you're predicting product properties, so you kind of see a pattern here. And so H2O plus AgI is Ag2O plus HI. Double displacement here. Okay, so balancing each of these. As we go through. So 2. Oops, sorry. 4, 2, 2. Oh, sorry. I made a mistake. It's COBr4. Cobalt 4 sulfate, because the whole sulfate's 2 minus. So cobalt in this case had to be 4 plus. So, my mistake. So this is double displacement. And 10. LiNO3 plus Ag. This is kind of one of those rare single replacement ones, so I'm going to box it again this time to make sure you see what we're doing here. Li plus 1, NO3 minus 1. Ag is normally a positive 1 charge when it is bonded. So we crisscross here, and we get AgNO3, and then since Li is by itself, we don't write a charge on it. It's just an elemental form. If it were Cl or F, then it'd be Cl2 or F2, because those are diatomics. Next unit is the mole. And with mole, we start really introducing the mathematical aspect of chemistry, and our calculations kind of evolve from the basis of this. And so as we kind of go through the problems, you'll see a lot of different conversions and things like that that are important for these processes. But the first question is just defining a mole. And 1 mole is equal to 6.02 times 10 to the 23rd units. So notice that there's no unit for mole. It's whatever unit you want to put for it. So if you say a mole of eggs, then that's 6.02 times 10 to the 23 eggs. If you say a mole of atoms, then that's 6.02 times 10 to the 23 atoms. So whatever you label the mole as, that's 6.02 times 10 to the 23 of that. So make sure that you are remembering that conversion and how it can be used in a lot of different scenarios, because everything that represents a mole, everything that's measured by the amount in moles is equal to 6.02 times 10 to the 23rd. So the first few problems are kind of one-step calculations. And so with this, I'm going to do a few of them in fact label and a few of them with proportion method to make sure that we are seeing both ways to do these types of problems. So for number 2, we start with 34 grams of CuOH2, and we'll do this as a fact label. And so what we want to do here is we want to just convert to moles. And when we convert to moles, what we use is the molar mass, which is the mass in grams based on the periodic table for CuOH2. So notice this conversion is also another conversion to make equivalent to 1 mole. So 97.57 grams of CuOH2 is the equivalent of 1 mole. And so when you divide by that, you get 0.35 moles of CuOH2. And again, to make sure you're dividing and multiplying the right way, your answer needs to make sense. And so with this, I know my mass that I have is less than the molar mass, which means the moles I have of it should be less than 1. So this is kind of a very basic way to kind of check to make sure that you're doing it correctly. Okay. 3. How many moles are present in 2.45 times 10 to the 23rd molecules of CH4? Well, we know that there's 6.02 times 10 to the 23rd molecules of CH4 for 1 mole of CH4. So we can set up a proportion in this way to figure out X moles of CH4. Okay. Don't forget, when you're typing this in your calculator, the best way to do it is to use second comma to get that small capital E. Okay? Because what that does is it puts a parentheses around that number as one thing. So you don't have to do parentheses anymore because it makes it one number. So that way you don't have those issues with your calculator interpreting your number input differently. So again, here we get 0.41 moles of CH4. And again, because our number is 2.45 times 10 to the 23, excuse me, that's less than 6.02 times 10 to the 23. So our answer in moles should be smaller than 1 mole. Okay. 4. How many grams are there in 3.4 times 10 to the 24 molecules of NH3? Well, we have to start with molecules of, NH3. And we must convert that to moles first. And so we know 6.02 times 10 to the 23rd molecules, is equal to 1 mole of NH3. And 1 mole of NH3 is equal to 17.04 grams of NH3. So with the fact label method, the units cancel out, and you're left with grams of NH3. And in this case, it's 96.24 grams of NH3. For 5, how much does 4.2 moles of CaNO32 weigh? Well, 4.2 moles of CaNO32, well, 1 mole of CaNO32 has the mass of 164.1 grams of CaNO32. So we can set a proportion here. Notice in the proportion method, the units are across from each other. They're not diagonal like in fact label when you're multiplying things. You have an equal sign here, so an equal sign means that the information on the left has to be equivalent to the information on the right, so the units are kind of on the same position across the equal sign. Okay. So here we do this and we figure out that it's 689.22 grams of CaNO3 2. 6 is a very kind of fundamental molar mass problem, just to make sure that you know how to calculate the molar mass of a compound. Technically, you should have been able to do that in the previous problems, but this is just kind of a straightforward problem to make sure that you know how to do it. MgO, the mass of Mg is 24.31 based on the periodic table. Oxygen is 16.0, so it is 40.31 grams per mole. If you notice, I'm going to try to encourage you to write your exponents as negative for moles in this case instead of over grams per mole / mole like in the answer key, just because the IB is going to really encourage you to do that moving forward. The next section is empirical formula. And what you need to remember is that for empirical formula, your goal is to always convert the amount of each element you have into a unit that is comparable amongst all of them. And the only unit that is equitable in comparison is the mole. So your job is always to convert your grams or your percentages into grams and then into moles by using the molar mass. And so when we look at a problem like this, when we're given 65.5% by mass of carbon and 5.5% mass by hydrogen and 29.0% mass by oxygen, because these are percentages, they are out of 100. So if we had 100 grams of this sample, that's safe to say that you have 65.5 grams of carbon, 5.5 grams of hydrogen, and 29.0 grams of oxygen here. And now that you have the grams, the thing is 1 gram of carbon doesn't contain the same number of atoms as 1 gram of hydrogen or 1 gram of oxygen. So what we do is we have to make it the equitable unit. And the equitable unit is moles. And so we divide each of these by their molar mass. Okay. And what we get is 5.458 moles, 5.446 moles, and then 1.813 moles. I really encourage you not to round very much here, because if you round too much, your answers will be off because your decimals don't carry on throughout the entire problem. So I try to keep as many decimal places as I can in these problems to make sure, because these empirical formula problems are designed to work out. So if you get very weird answers, it's very unlikely that that's correct for these type of problems. So the first thing you do is divide by the molar mass. The second thing you do is divide by the smallest number. So we divide them all by 1.813 because we're trying to find a ratio between all these elements. And so we end up getting 3, approximately 3, 3, and 1. So our empirical formula is C3H3O1. You don't have to write the 1. I'm just writing it there just to kind of make sure that you see where that came from. Now, in this case, all the numbers here were even, like integers, and so we didn't have to do anything else. If one of these numbers is not an integer, then you may have to multiply by a number to get rid of that decimal. So let's say you had a 2.5, a 3, and a 1 in your answer here. You'd have to multiply all of them by 2 to get rid of that 0.5. But that's a possible step that may be needed sometimes. So just keep that in mind about that. Now, 2 is an extension of that problem, asking for the molecular formula. So the molecular formula, this is the empirical formula. The molecular formula is always a multiple of the empirical formula ratio. So it is some form of carbon, hydrogen, oxygen that reduces down to 3 carbons, 3 hydrogens, and 1 oxygen. So it could be 6 carbons, 6 hydrogens, and 2 oxygens. It could be 30 carbons, 30 hydrogens, and 10 oxygens. Those are all molecular formulas of C3H3O's empirical formula. In fact, C3H3O could be a molecular formula as well. It's not always, but it could be. Since the formula is just a multiple of itself, the mass is also a multiple of itself. And so if the problem gives you that the mass of the molecular formula is 110 grams per mole, and we know C3H3O1 weighs 55.1 grams per mole, that means that the molecular formula is 2 times as big as the empirical formula. So therefore it is C6H6O2. And you can double check by calculating the molar mass of that, and you will get approximately 110 grams. 3, this is another kind of continuation of empirical formula, another practice one, where you have 18.7 grams of lithium. I'm going to convert percentages right to grams right away so we don't have to rewrite them again. 16.3 grams of carbon and 65.0 grams of oxygen. We divide by each molar mass, which is 6.94, 12.01, and 16.00 grams. And we end up getting 2.69 moles of lithium, 1.357 moles of carbon, and 4.0625 moles of oxygen. You divide them all by 1.357, and you get 2, 1, and 3. So your overall formula, empirical formula here is Li2CO3. Now it continues and asks you what the molecular formula if the molar mass is 73.8 grams per mole. Well, if you divide that by the molar mass of Li2CO3, it also happens to be 73.8 grams per mole. So therefore, that means it is 1 times that. So it is the same as the empirical formula given here. And 5, 6, and 7 are very kind of additional practice of the same concept of converting empirical formula to molecular formula. And so for 5, you would take 88 grams per mole, which is given to you in the problem, and you'd calculate the molar mass of C2OH4. So that's 24 plus 4 plus 16 is 44. So that means it's 2 times as big. So your formula is C4O2H8. Number 6, you have a molar mass of 136, and you have an empirical formula of C4H4O, which ends up being 68 grams. And that ends up being 2 times as well. So your molecular formula is C8H8O2. Seven, same idea, 254.7 grams per mole over 126.92 grams is the molar mass. So you get 2 times. So your molecular formula is C2F2Br2O2. Eight, 9, 10 continue this concept of empirical formula, including some percent composition in there as well. So number 8 is a continuation, is an additional problem. 39.9 grams of carbon, 6.7 grams of hydrogen, and 53.4 grams of oxygen. We divide by 12.01 grams, 1.01 grams, and 16.0 grams, and we get 3.32 moles, 6.63 moles, and then 3.34 moles. We divide them all by the smallest number, and we get 1, 2, 1. So the empirical formula is CH2O. But the molecular mass is 60 grams per mole, and the empirical formula's mass is 30 grams. So that means it's 2 times, so it's C2H4O2. Now, I know all of these problems that we have in the review sheet happen to always be times 2 or times 1, but that's not always true. That's a coincidence. Don't just assume that because every single problem on here was times 2 that your answer is going to be times 2. 10 is calculate the mass percent of carbon, nitrogen, oxygen in acetamide. Okay? So that is C2H5NO. So mass percent is the mass of each element total in that compound divided by the total mass of the compound. So the total mass of this compound is 59.08 grams. So for carbon, there's 2 carbons, so that's 2 times 12.01 over 59.08 times 100 gets you 40.66%. N is 14.01 over 59.08 times 100 gets you 23.71%. H is 5 times 1.01 over 59.08 times 100, which gets you 8.55%. And then O is 16.00 over 59.08 times 100, which gets you 27.08%. And now you've done it right if all your percentages once you've added up, is approximately 100. Yes, a little bit of rounding here or there might affect your numbers, but overall you should be fairly close to 100% in after you've calculated all of these. The next section of this unit has to do now with stoichiometry. So now we've gone away from 1 and 2 step conversions, and now we're converting from one substance in a reaction to another substance in a reaction. And so here you're actually going to have to use what's called the mold-to-mole ratio. And that mold-to-mole ratio is really important when you're converting from one substance to another in the problem. So I'm going to alternate doing these problems with the proportion method and the factor label so that you can see both ways to do this. So the first question in here is given that 2NaOH plus H2SO4 yields 2H2O plus Na2SO4. Sorry. Okay. Now, it says how many grams of sodium sulfate, that's Na2SO4, will be formed if you start with 200 grams of sodium hydroxide and you have excess sulfuric acid. They give you the word excess to make sure that you understand that it is not a limiting reactant problem. So this is an excess, so we don't care about this amount in our problem. And so here we will take our 200 grams of NaOH and first, like we always do, convert it to an equitable unit. And that equitable unit is always moles. So it turns out it's 40.0 grams of NaOH is equal to 1 mole of NaOH. Now that you've got moles of NaOH, now you can do the mole-to-mole ratio. And there's 2 moles of NaOH for every 1 mole of Na2SO4. That gets rid of the moles of NaOH. Now you're at moles of Na2SO4. And then 1 mole of Na2SO4 is equal to 142.04 grams of Na2SO4. So the moles now cancel and you're left with grams. And you should get approximately 355.1 grams of Na2SO4. Number 2. Okay. Given this equation of Pb SO42 plus 4LiNO3 yields PbNO3 plus 2Li2SO4, it says how many grams of lithium nitrate are needed to react to make 250 grams of lithium sulfate. Now, it doesn't matter which side of the reaction you start on or which side of the reaction you end on. As long as the two substances are in the same reaction, you can convert between them. So they could both be reactants, both be products, one be a reactant, one be a product. It doesn't really matter. So, just like the same problem before, we have to convert our grams into moles. And it turns out that 109.94 grams of Li2SO4 is 1 mole of Li2SO4. Okay? And so, with this, 250 divided by 109.94 gets you 2.274 moles of Li2SO4. Now, that 2.274 moles of Li2SO4 needs to be converted into LiNO3. And the mole-to-mole ratio is 2 moles of Li2SO4 to 4 moles of LiNO3. So really, you're doubling this. So we're going to double this here. And we're going to realize that you need 4.548 moles of LiNO3. Now, with the 4.548 moles of LiNO3, we need to convert back to grams. So 1 mole of LiNO3 has a mass of 68.95 grams. So now we cross multiply that. And then so we multiply this by 68.95 0.95. And we should get 313.58 grams of LiNO3. Another problem with the stoichiometry, here we have Fe2O3 plus 3H2 yields 2Fe plus 3H2O. Okay, how many grams of iron, so question mark grams of iron, can be made from 16.5 grams of Fe2O3? And we're assuming hydrogen is in excess because it wasn't given to you in the problem. Again, if you notice, one of the things I try to do when I do my workout and I'm doing these videos is I try to put everything down on paper. All the information, I try to organize it. I try to make it on the paper so that when I see it, I'm less likely to misremember something or make a silly mistake. The silly mistakes that happen are when you try to keep something in your mind and you're doing the problem and then you get it mixed up in your mind. But if it's on the paper, you're less likely to mix up the numbers or mix up the units and things like that. So I try to write everything down on the paper here so you see my reasoning and my logic for this. And so here we have 16.5 grams of Fe2O3 and we're solving for grams of Fe. So we need to first convert this to moles of Fe2O3. So then you convert 1 mole of Fe2O3 to 2 moles of Fe. And then 1 mole of Fe is 55.85 grams of Fe. And you'll end up getting 11.54 grams of iron. Okay. Now, the next set of problems on here are what are known as limiting reactant problems. And limiting reactant problems are ones where you have amounts of both reactants, so one of them is going to run out. And when that one runs out, then that will limit how much product you can make. Now, to simplify things for us, I've always kind of done it in maybe a little bit longer way, but it's a consistent way of solving this problem. And so what I do is I take each amount of reactant and I take it and I convert it to one of the products. As long as it's the same product, it doesn't matter which one. Sometimes the problem will tell you which product you want, and then you just solve for that one, then you get your answer for limiting reactant and the answer for your problem at the same time. But whichever reactant makes less of that product is your limiting reactant, and that's how much product you can make. So in this example here, for number 1, we have a equation that needs balancing. As such. So it asks which reactant is limiting, assuming we started with 30 grams of ammonium nitrate and 50 grams of sodium phosphate. Okay, so we started with 30 grams of this and then 50 grams of sodium phosphate. And it says what is the mass of each product formed. And so therefore I ended up solving for NaNO3 to figure out which one's the limiting reactant. And then whichever one is the limiting reactant, I would solve again for NH4,3PO4. Okay, so that's what the work looks like on here on the answer key. And so here I will do 30.0 grams of NH4NO3, and I will do proportion method here, and I will say that 80.06 grams of NH4NO3 is equal to 1 mole of NH4NO3. And so then that gets us 0.3747 moles, and then 0.03747 moles of NH4NO3 is equal to 3 moles of NH4NO3 over 3 moles of NaNO3. So it's the same amount, 0.3747 moles of NH4NO3. Now we have to convert that back to, oh sorry, NaNO3. I misspoke. I just copied the top one. NaNO3. So this is This is NaNO3. And that 1 mole of NaNO3 is the equivalent of 85 grams of NaNO3. So therefore, this times 85 gets you possibly produce 31.85 grams of NaNO3. Now, we have to look at how much the other substance could make, and then that way we can see which one actually makes less of the product. So this is one possible answer here. The other possible answer, and I'll do this as fact label, is 50.0 grams of Na3PO4. Convert to moles. So it is 163.94 grams of Na3PO4 is equal to 1 mole of Na3PO4. And so 1 mole of Na3PO4 is equal to 3 moles of NaNO3. And then 1 mole of NaNO3 is equal to 85 grams of NaNO3. So I will type that in the calculator really quickly. 50 over 163.94 times 3 times 85 gets you 77.77 grams of NaNO3 possible. So because the 30 grams of NH4NO3 makes less NaNO3, that is your answer, and NH4NO3 is the limiting reactant because it makes less product. So you're going to make 31.85 grams of NaNO3, and then you're going to stop because there won't be any more NH4NO3 available to react. And so that's the really key thing here. So now that you know NH4NO3 is the limiting reactant, you can now then solve for how much NH4,3PO4 that you could make. And so you would do it as just like you did before. You'd start with the 30 grams of your limiting reactant. And I'm going to do the proportion method here. So here you would still just do it as 80.06 grams of NH4NO3. And it's 1 mole of NH4NO3. And you'd get the same 0.3747 moles. And that 0.3747 moles of NH4NO3 is equal to, here, 3 moles over 1 mole of NH4,3PO4. So now we have to divide by 3 to get the actual moles of that. So we divide by 3, and we get 0.1249 moles of NH4,3PO4. And then we take that 0.1249 moles of NH4,3PO4, and we convert it to grams. So the mass is 146.09 grams. And so if we multiply that by 146.09 grams, we get 18.25 grams of NH4,3PO4 that could be made as well. Now, if you're curious, there is an excess reactant remaining problem. We didn't end up really doing that, and that won't be on the final exam. But for those of you that are curious, I think we did discuss it, but we never were tested over it. And it says, what mass of the excess reactant is left over? Well, the way you do that is you take your limiting reactant and you solve for the excess reactant used. So you're trying to figure out how much of the excess reactant was used, and you subtract that from how much you started with. And so here you would start with your 30 grams of NH4NO3, and you would calculate, well, how much of my other reactant would I need to react with 30 grams? So now we do another stoichiometry problem. And there's 3 moles of NH4NO3 to 1 mole of Na3PO4. And then 1 mole of Na3PO4 is 163.94 grams. So then we end up getting 20.48 grams used. So then if we started with 50 grams, we subtract that, and there's 29.52 grams of Na3PO4 remaining. So that's how much didn't react, because there wasn't enough of the other reactant to get it. Okay. And number 2 is the same type of problem. Okay. So for 2, we have CaCO3 plus FePO4 yields Ca3PO4 2 plus Fe2CO3 3. So we have to balance here, and so we end up putting a 3 and a 2 here to balance that. Okay. So we're saying we start with 100 grams of calcium carbonate and 45 grams of iron 3 phosphate. So what is the mass of each product that can be formed? Okay, so we will do our calculations again, and we will have that here. So 100 grams of CaCO3, we'll do this one as factor label. So the molar mass is 100.09 grams of CaCO3. So that's 1 mole of CaCO3. 3 moles of CaCO3 is 1 mole. I believe we just chose Ca3PO42 as the product in question for this, because we had to solve for both of them anyways. So then 1 mole of Ca3PO42 has a mass of 310.18 grams. So this can make 103.30 grams of Ca3PO42 if it all reacted. Now conversely, if we start with 45.0 grams of FePO4, well, 150.82 grams of FePO4 is the equivalent of 1 mole of FePO4. So this is 45 divided by 150.82 gets you 0.298 moles of FePO4. So we can continue that on to the moldable ratio. So it is 2 moles of FePO4 to 1 mole of Ca3PO4 2. So we have to divide that by 2. And we get 0.149 moles of Ca3PO4 2. So then we take that, and then we convert it to grams. 1 mole of Ca3PO4 2 is the equivalent of 310.18 grams, like the last part. So then we get this times 310.18. So we get 46.27 grams of Ca3PO4 2 that could be made. So notice that this number is smaller than this number, so therefore FePO4 is your limiting reactant. Okay. So now that we know the amount of Ca3PO42, we can now take the 45 grams of FePO4 and convert it to Fe2CO33. And so here we will take 45.0 grams of FePO4, and it's 150.82 grams of FePO4 is 1 mole of FePO4. Well, it is 2 moles of FePO4 to 1 mole of Fe2CO33. And then 1 mole of Fe2CO33 is the equivalent of 291.73 grams of Fe2CO33. So then we get 43.52 grams of Fe2CO33 could also be produced. So you could produce 46.27 grams of Ca3PO42 and also produce 43.52 grams of Fe2CO33 at the same time. Again, the excess reactant one, I'm going to solve it even though you don't need to know how to do it, so you can skip this. But for some of you that are really curious and that want to know how to solve it, you would take the same thing. You take your limiting reactant FePO4, you'd convert it to moles. So it's what? 45 divided by 150.82. So that's 0.2983 moles. And then we now convert it to the other reactant. So 2 moles of FePO4 is 3 moles of CaCO3. So that's 0.2983 moles of FePO4. And so then we multiply by 3, divide by 2, and we get 0.4476 moles of CaCO3. And we convert that into grams so we can figure out how many grams were used. 1 mole of CaCO3 has a molar mass of 100.09 grams. And so therefore you end up getting 44.80 grams of CaCO3 used. So therefore it's 100 minus 44.80 grams. So you have left over 55.20 grams of CaCO3 remaining. So that's how much didn't react because you ran out of the other reactant. Okay. One last problem here, again, to do limiting reactant. Just this, again, I know it sounds very repetitive, and I know because I'm doing every single problem along here on the video, but we wanted to make sure that you had several problems so you could practice it, and that if you struggled with one, you could learn how to make sure you could review and learn, and then have another practice problem available. So do I really expect you to do the entire thing? No, not necessarily. If you can do the first problem of this or the second problem of this, then you don't need to do the third problem. But it's always good practice, and those of you that are really worried that you're going to make silly mistakes and things like that, the more practice, the better. The less likely that you're going to make a silly mistake if you've been doing it more and more often. Okay? So number 3. Okay? Write the balanced equation for the reaction given below. So it is CuCl2 plus 2 NaNO3 yields CuNO3 plus 2 NaCl. Okay, so that's balanced. So if you have 15 grams of copper 2 chloride, so it's 15 grams of this, and 20 grams of sodium nitrate, how much sodium chloride can be formed? So we want to figure out, in this problem, just the sodium chloride. So ignore the CuNO3 and just solve for the sodium chloride. And so here, we can take the 15 grams of CuCl2 and convert that to moles by using the molar mass. And then doing the moldable ratio, 1 mole of CuCl2 makes 2 moles of NaCl. And then 1 mole of NaCl has a mass of 58.44 grams. So this could make 13.04 grams of NaCl if all of it reacted. With the 20 grams of NaNO3, I'm going to do proportion method. 1 mole of NaNO3 is the equivalent of 85 grams of NaNO3. So you get 20 divided by 85 gets you 0.2353 moles of NaNO3. So then you take that 2353 moles of NaNO3 and we convert. So 2 moles of NaNO3 makes 2 moles of NaCl. So it's the same amount, 0.2353 moles of NaCl. And with this, we can then convert the moles of NaCl into grams, because 1 mole of NaCl is 58.44 grams of NaCl. So then we multiply this by 58.44, and we find out that it is 13.75 grams of NaCl. So NaCl 13.04 is less than 13.75, so therefore CuCl2 is your limiting reactant, because it makes less NaCl possible. And a little add-on to this question was a percent yield. And so if 11.3 grams of sodium chloride were produced in a reaction, what is the percent yield? Well, 11.3 is your experimental, and your theoretical, we found out, is 13.04 grams, because that's what we calculated here. So that times 100 would get you 86.66% yield. Okay, going over the last 2 units for the final exam now. Okay, the second to last unit is acids and bases. Now, with acids and bases, you're looking at kind of the fundamental concepts, the definitions, a few calculations, but a lot of it is conceptual. And so you'll notice from kind of the review sheet what type of things that we're expecting you to know. So what forms when an acid reacts with a base? It forms salt and water. And the salt, just for reference, is any ionic compound. It is not the way we refer to as salt as sodium chloride. A salt is any ionic compound. 2, substance that turns blue litmus paper red, neutralizes bases, and tastes sour, that would be an acid. The opposite one, red litmus paper blue, that would be your base. Okay? Only group 1 and group 2 metals react vigorously with hydrochloric acid. So here we're looking at group 1 or group 2 metals, and that would be Mg in this case. So here we don't have to write the word strong, but we're just kind of identifying the properties here. So conducts electricity and feels slippery, that would be a base. If it conducts electricity really well, then it's a strong base. Conducts electricity and reacts with metal, that's acid. Blue litmus paper red, that's acid. And reacts with an acid to produce a salt, that would be a base. So with this section, we're just kind of identifying what type of substances we have. HF is an acid. You'll notice most acids start with a hydrogen. NH4Cl is a salt because it has a polyatomic in it and another ion as well that's not H. C, KOH, is a base because ionic compounds that end in OH are generally bases. D, is an acid, starting with H again, and E is a salt. The next section has to do with writing kind of what happens in each species when it reacts with water and it dissociates. So for example, here acids will react with water to form H0 plus and NO3 minus, which is your conjugate base. HBr, another acid, will do the same thing. H3O plus Br minus. The strong bases don't even necessarily need water in the reaction to react. They just simply break up into their ions. The last part of reactions is writing acid plus base neutralization reactions. And so these aren't any different than any other double displacement reaction. It's just that you specifically get water as a product here. And you have to still make sure that your products make sense. So CA's plus 2 or 2 plus, so it should have NO3 2. And so we have to balance this to finish that. H2SO4 plus KOH yields K2SO4 because K is plus 1 and SO4 is 2 minus. So this balances as well. With the calculations, you really want to focus on a couple of things. You want to focus on the concept that pH equals negative log of your H plus concentration, and which conversely also means POH is equal to negative log of OH minus concentration. And you can rearrange this to get H plus is equal to 10 to the negative pH, and conversely OH minus equals 10 to the negative POH. And for our purposes, at standard temperature, pH plus POH equals 14. And those are really the 3 or 5 major equations that you should know for this. But really, if you look at this, what you're looking at is really just knowing this equation, and this equation. Because the OH equations are identical to the H equations, except you just have OH instead of H in there. So minimize what you have to memorize in that scenario. So for 1A, so we have H plus concentration of 1.0 times 10 to the negative 5. Okay, so just to review, again, typing in your calculator, you want to type negative, not subtract, but negative log of 1.0 second comma e to the negative 5. And so you get 5 here for your pH, which means your POH will be 9 because it adds up to 14. B, your OH concentration is equal to 3.0 times 10 to the negative 8. So here we would do negative log of 3, second comma, negative 8. Now, because that's OH, what you got in your calculator is your POH, which is 7.52. Which makes sense because whenever you take the negative log of a number and then the exponent's negative 8, the number is going to actually be a little bit less than 8. So then your pH is equal to 6.48. C, here we have H plus is equal to 2.5 times 10 to the negative 2. So then that's, again, negative log 0.5 second comma negative 2. So your pH in this case is 1.60 and your POH is 12.40. Continuing on, OH concentration is equal to 7.5 times 10 to the negative 3. So here, when you take the negative log of it, you've just got to be careful that it's 7.5 second comma negative 3. which is POH of 2.12. So your pH is equal to 11.88. E, H plus, is 1.2 times 10 to the negative 14. So negative log of 1.2 E negative 14. That gets you a pH of 13.92, which means a POH of 0.08. Last question. H plus is equal to 6.0 molar. So then this is just negative log of 6. And you are technically allowed to have negative pHs. Now, they're not usually common, but the scale does go in both directions quite extensively. But for most common household items, 0 to 14 is significant enough, sufficient enough for the range. Okay. Now, with the second part here on number 2, here you have a variety of pH and pOHs, and you're reverse calculating it. So you're taking your pH and then converting it back to your H plus or your OH minus concentration. So the way I do this is, if I know pH is 3.0, then I know my pOH is 11. So my H plus concentration is 10 to the negative 3. My OH concentration is 10 to the negative 11. So this is 1 times 10 to the negative 3, and this is 1 times 10 to the negative 11 for your OH and your H plus. For B, pOH is 2.60, so pH is equal to 11.40. So this is 10 to the negative 2.60, 10 to the negative 11.40. 10 caret negative 2.60. And you get 0.0025. And then you do the same thing with your H plus, and it's 3.98 times 10 to the negative 12 of your OH and your H plus. Really important to keep track of what you're talking about, OH versus H plus. That's where students make the most mistakes with this, because they forget that if you have pOH, then you solve for OH. If you have pH, you solve for H. That's the most common mistake that students make. So notice that I'm very deliberate about writing out each of these things. pOH is equal to 5.63. pH is then equal to 9.37. So 10 to the negative 5.63, 10 to the negative 9.37. 2.34 times 10 to the negative 6, and then 10 to the negative 9.37 is 4.27 times 10 to the negative 10 as your OH minus and your H plus. Continuing on. Let's see. Okay. Again, pH is equal to 7.51, so your pOH is equal to 6.49. So 10 to the negative 7.51, 10 to the negative 6.49. And I've already got this done already, so I'm going to calculate this using that. So it says that 3.1 times 10 to the negative 8, and then 3.2 times 10 to the negative 7 is your H plus and your OH minus. Now, last couple, pOH is negative 1.13. So your pH is actually equal to 15.13. Had to do a double take right there for a second. So 10 to the negative 1.13 and 10 to the negative 15.13 gets you 13.49 molar, and then 7.41 times 10 to the negative 16. So you can see with this, you can get a variety of different numbers here for this same concept. So there isn't necessarily a right number or a wrong number here, as long as you're doing everything correctly. Let's see, OH minus H plus. So that's the extent of acid base that you need to know for the test. So knowing the concepts and then knowing the calculations for this. The last unit that we covered, mostly during remote learning, was gas laws. And so just a reminder, this should still be fresh in your mind, but we're still going to work out these problems to make sure that you understand the expectations here. And so if 22.5 decimeters cubed of nitrogen at 748 millimeters mercury is compressed to 725 millimeters mercury, so I write out volume 1 is 22.5 decimeters cubed, pressure 1 is 748 millimeters mercury, pressure 2 is 725 millimeters mercury, and volume 2 we don't know. What is the new volume? Well, here we can think of it as the combined gas law to save ourselves some time and just say, well, temperature's not present. So we just plug this in. 22.5 decimeters cubed times 748 millimeters of mercury is equal to X times 725 millimeters of mercury. Okay. Divided by 725. And you get X is equal to 23.2 decimeters cubed. Okay, does that answer make sense? Yes, it does, because your pressure went slightly down, so your volume should go slightly up. And so that's consistent with our concepts. 2, a gas with a volume of 4.0 decimeters cubed and a pressure of 205 kPa is allowed to expand to a volume of 12.0 decimeters cubed. And then what is the... Let's see. What is the final pressure? Okay. Notice that when I'm reading the questions here, I write all my numbers out and I label them, so I can kind of keep track of which one's my volume 1 and pressure 1 and things like that, because I think it makes it easier to organize and then evaluate the information that's given. So again, same one, P1V1 equals P2V2. So 4.0 decimeters cubed times 205 kPa is equal to 12.0 decimeters cubed times X. Notice that as long as the units are the same, it doesn't matter what unit that I have it in. So I end up getting 68.33 kPa. You just got to remember that the unit that you are using gets carried over. So if I have kPa on one side, then my X on the other side must be kPa as well. That's just kind of a good reminder. Okay. 3, a 40.0 decimeter cube tank of ammonia has a pressure of 12.7 kPa. Calculate the volume if the pressure is changed to 8.4 kPa. Again, 40.0 decimeters cubed times 12.7 kPa is equal to 8.4 kPa times X. So then you end up getting X is equal to 60.48 decimeters cubed, which makes sense because the pressure's going down, so the volume has to go up. And the pressure's going down by about 50%, so the volume goes up by about 50%. Okay. 4. Okay. A container containing 5 decimeters cubed of gas is collected at 100 degrees Kelvin, and then allowed to expand to 20.0 decimeters cubed. What must the new temperature be? Now, the key thing here is that you'll notice whenever I do any of these problems that I always convert my temperature to Kelvin as soon as I get it. In this problem, they've been nice enough to do that for you, so you don't have to worry about it. So you use combined gas law, pressure is not here, so it's just V1 over T1 equals V2 over T2. V1 is 5 decimeters cubed, T1 is 100K, V2 is 20 decimeters cubed, and then this is X Kelvin. So we cross multiply, and then X equals 400 Kelvin. Technically, you could convert back to Celsius, but it doesn't specify which unit you have to have the answer in, so it doesn't matter. Okay, 5. A gas occupies 900 centimeters cubed at a temperature of 27 degrees Celsius, which is 300 Kelvin, because you always add 273 to it. So notice I convert right away so I don't end up accidentally using my temperature in Celsius. What is the volume at the temperature of 132 degrees Celsius, which is 405 Kelvin? So then this is 900 centimeters cubed over 300 Kelvin is equal to X over 405 Kelvin. And X ends up being 1,215 centimeters cubed. Now, a couple of problems to go with ideal gas law, where you're not changing conditions, you are just trying to figure out how much gas or what conditions are necessary to have that certain amount of gas. And so the thing here, though, is you have to have certain units for ideal gas law. Ideal gas law is PV equals nRT. For us, this has to be in kPa, decimeters cubed, moles, Kelvin, and then 8.31 joules per mole per Kelvin for R. Okay. So we write everything that we have down, and then we solve for it. So 6 tells us that we have 4 moles of gas, which is N. We have a pressure of 567.4 kPa, so that's P. And we have a volume of 12.0 decimeters cubed. So it asks what is the temperature. So PV equals nRT. T will equal PV over nR. So then that is 567.4 kilopascals times 12.0 decimeters cubed over 4.0 moles times 8.31 joules per mole Kelvin. And that equals our temperature. And that means our temperature is 204.84 Kelvin. Again, they didn't say which temperature unit, so you can leave it as 204.84 Kelvin. They asked it in Celsius, then you would subtract 273 from that. So you'd get like negative 68.16 degrees Celsius. Okay. 7. If I have an unknown quantity of gas at a pressure of 121.59 kPa and a volume of 31 decimeters cubed and a temperature of 87 degrees Celsius, which ends up being 360 Kelvin. How many moles of gas do I have? Okay, so PV equals nRT. And so 121.59 kPa times 31 decimeters cubed is equal to N times 8.31 joules per mole Kelvin times 360 Kelvin. Looks like I don't have the answer on the key for this, so I will type it in right now. Oops. Times 31 divided by 8.31 divided by 360. And we get N is equal to 1.26 moles of gas. Last couple of problems here we have are the gas law equations. Okay, and so one, here we're doing just an STP for these practice ones. And so what's nice about that at STP is that 1 mole of any gas is equal to 22.7 decimeters cubed. Okay, so you can use that as a conversion factor for these problems, like you would molar mass or Avogadro's number. So in this problem, it says calcium carbonate decomposes into CO2 plus calcium oxide. How many grams of calcium carbonate will I need to form 3.45 decimeters cubed of CO2? Well, 3.45 decimeters cubed of CO2 we convert into moles, knowing that 22.7 decimeters cubed of CO2 is 1 mole. And then that 1 mole of CO2 needs 1 mole of CaCO3. And then 1 mole of CaCO3 is the equivalent of 100 grams of CaCO3. So we end up getting, and I did not record this answer for some reason, 15.20 grams of CaCO3 needed. Two, last problem. Here we have 1.25 decimeters cubed of ethylene gas, which is C2H4. Okay, how many liters of water can be formed, of water vapor can be formed with this? Now, we're going to convert like this. So 1.25 divided by 22.7 is equal to 0.055 moles of C2H4. And it is a 1-to-2 ratio. One mole to 2 moles of water. So then we double that. 0.1101 moles of water. And then we convert that back. 1 mole of H2O is 22.7 decimeters cubed. So we multiply by 22.7 and we get 2.5 decimeters cubed. Now that's not a coincidence. It turns out because the molar volume is the same, really all we had to do was the mole to mole ratio here. But so the answer for this is 2.5 decimeters cubed. Okay. One more problem. Number 3. 2Cl2 plus C2H2 yields C2H2Cl4. Now, this one incorporates gas law, ideal gas law with the molar volume, and also our normal stoichiometry here. So we start with 75 grams of this, okay, of C2, or how much we produce that. So when we have 75 grams of C2H2Cl4, we convert that by using the molar mass into moles of C2H2Cl4. And for that, it would be 12.01 times 2 plus 2.02, which is 2 hydrogens, plus 4 times 35.44. So that's 167.8 grams of C2H2Cl4. Well, our moldable ratio is 1 mole of C2H2Cl4 to 2 moles of Cl2. And 1 mole of Cl2 is 22.7 decimeters cubed. We're assuming at STP unless otherwise stated. 2 times 22.7. Okay. And that gets you 20.29 decimeters cubed of chlorine gas. And that is the end of the final review key. If you have any questions, feel free to email me, and I will get back to you as soon as possible. Best of luck on the exam on Tuesday.